the section we're in, we're going to be finishing out 10.5 today. I want to make sure that we at least know kind of, the actual necessary parts that we're doing here, so that we know each type of problem that you feel comfortable with them. So I'm going to kind of roughly go through stuff. Okay. A little light. That's time today.
What?
Unless I hear otherwise. All right. Okay, today on section 5, 10.5. This will be the last day of it. Tomorrow we're going to move on. As I kind of warned you this week, at some point the end of the week, possibly Friday or maybe if you carry over to Monday, we'll be doing review for the chapter test coming up. Chapter test for us is next Tuesday or Wednesday. It's kind of that time frame, and then after that, then we'll be going into maps testing. So keep that in mind. That's kind of our schedule for next week. But 10.5, what we're going to talk about is tangents, right? That's kind of the main part. Yesterday we introduced a new word, which was a secant. So that was something that we discussed yesterday. The goal today is just do a few examples of each of those theorems. I'm just going to go right into that, and that way we can get right to the work, because I only have you for about a half an hour or so. But examples are going to be based on theorem 10.10, put the word theorem here, and theorem 10.11. So these are going to be my two examples I want to cover today, just to make sure you know exactly how to do your homework today. Once we're through that, we're going to do a quick check to see kind of if you're ready to go on that. I want to see kind of where you're sitting, see if you know the types of problems and whatnot, and then we'll get into the homework. And we do have new homework today, so hopefully that makes sense. So new homework, it'll be due this Friday. So, which it's not that bad. It's actually pretty easy if you understand what we've been doing the last couple days in here. So new homework will be Friday. I think Friday is the 4th. May 4th. Okay, we're good though? Okay, perfect. Okay, let's go right into it. First one here. I have a circle. You have a center and a radius, and this is the point of tangency down here, and they draw a tangent line. What we talked about is that if this is truly a radius and that is truly a tangent line, these have to be at a perpendicular angle with each other. That was what 10.10 said. Now why that's important is that if you have certain lengths of these pieces, like let's say I'm looking for this piece, but I have the radius is 10, and I have this line down here is, let's go 12, we can find x. We can find the length of that hypotenuse wall, or any other wall that's been missing. I think one of the more interesting problems in the book was something like this. Instead of just finding that x, the length of the whole wall, they wanted this piece. Let's call this W. That's the piece they wanted. And that's clever, because it's basically two problems in one. We have to find the length of the whole wall that's missing. And once you have the length of the whole wall, then you can take whatever this number is, you subtract 10 off of it to find W. The reason why it's 10 can move, it's like a hand on a clock. So to find W, if you know this whole wall, subtract the radius off of it, which is 10. Which I thought was really kind of a clever way to do it. But let's continue with this problem. So how you do it, again, it's Pythagorean Theorem. It's a squared plus b squared equals c squared. A and c. And then you want to try to solve for the c, that long wall. So this is 10 squared plus 12 squared equals whatever that other wall was. I think I called it x earlier. It's called x squared. So this is 100. This is 121. Oh, not 121, but 144. We add those together, we get 244. And then what's the last step? Square root. Yeah. So you take the square root to this other side, and you take the square root of 244. Now, hopefully, everyone in here knows how to type that in a calculator, because like to get decimals. Square root button is usually around the function keys. It's usually have to hit like a second key or the shift key, and then hit one of the others. But I'm looking for the normal square root. I'm just going to type it in just so we have it. Square root of, so for me it's right around the number 7, but square root, it's about 15.6. 15.6. And that's the length of this whole piece right here. So this whole thing, from here to here is 15.6. Now, what's the length of W though? 5.6? Yeah. Because this is 10, and then you subtract it off of the 15, so this should be 5.6. Okay. Questions, comments about how to do it? Okay. I thought that was an interesting problem. It's just kind of one of those things you have to kind of notice how the 10 works, because I could definitely see people getting it wrong. They wouldn't see how to find it. All right, so that was the first one. Second type of question that we had from the homework was something like, let's see. Okay. This is an example I think I saw in the book, or something like this. There was kind of like a box-looking figure. There was a circle on the inside of it. It's supposed to be a circle, sorry, it looks like an oval, but okay, it's supposed to be a circle on the inside of whatever this object is. It somehow hit perfectly in all the corners. They have some certain numbers here. Let's go with this is 7. This is a 2x plus 8. This is a 3x minus 10. This is a 4. All right, and the question is, find x and find the perimeter. So there's two parts to these types of questions. That's how they always work. This particular picture needs to use theorem 1011. 1011, if you don't remember what that theorem said, is if you have a circle and you have points that are exterior of that circle, so like this point right here, that's exterior. When you draw tangents to the circle, so it hits the circle perfectly once, these two lines have to be equal to each other. So you can transfer the 5 down to here. That's how it works. That's how 1011 works. That works for every corner. Every corner's their own dot. So like if I go to the next corner over, this 4 can be put down here because this would be an exterior point, and the actual tangents to the circle would have to be the same. And same up here. But this is an exterior point, so the 7 can transfer. What about the last one though? Yeah, it's 7 equal, and actually solved it. Yep. So should be somewhat straightforward. Let's see. So setting those equals, so it's 3x minus 10 is equal to 2x plus 8. Subtract the 2x across, add the 10 across, because anything you move across equals 7, add or subtract. So this is 3x minus the 2x. This is 8 plus 10. So what is that? X equals 18. And then you gotta plug it back in and see what the walls are. So if you plug these back in, so if I go 2 times 18 plus 8, what is that? 36 plus 8, that's 44. And so that wall's 44, this wall would have to be 44. And now you have enough information that you can actually find the perimeter. So you could add up all the pieces on the outside to find the perimeter. So what is this? 12 plus 9 plus, this would be, what is that, 48. That's 51. And you can add up the walls. And that would be your perimeter. Because remember, definition of perimeter, just add up the outsides. So, questions, comments about the two problems we've been talking about the last couple days in here? That was really the newest type of problem. Okay, one of the last things I want to talk about was, I want to show you some pictures. Like I've been kind of hinting at these things for a while. I want to show you a picture of a gears on a clock to show you that idea of like internal tangent for circles. Show you external tangents, and there was this movie I kept referring to that had a bicycle that I talked about. Period 5 was all about it. They wanted to know more about the bicycle that was in this particular movie. It was called, Joseph Gordon-Levitt. It was about a bicyclist in New York that he was a mail carrier, and he made his own bike that had like a really big gear for the foot pedal, and then a really small fixed gear in the back, and the idea he could go really fast in the movie. The movie was terrible, but the bike itself was kind of a cool project. I like the math behind it. I think that was kind of the more interesting part of that movie, which is sad. But I want to show you pictures of that because I kind of hinted at that the last couple days, but I never really got to the picture. Never really showed you how it worked. So here's a couple of those pictures. Thought this was just kind of interesting. We should probably talk about it. All right. So first, I want to talk about gears on a clock. So So this is the inside of an actual watch. So it's a little excessive for what they have. But this is a picture that I found. I typed in pocket watch online, and this is the picture they showed. Tons of different mechanisms in there. You can definitely see that, you know, some of these circles are internally tangent, some are externally tangent, and how the gearing actually works and stuff, on how these switches work. But I would assume that some of these have to slide into place because like they're not connected. But like these two circles would be considered, like this small and this one here, they'd be considered externally tangent. Right? They're touching. If they were to slide into place, when one turns, the other one would turn at the same time. Same thing with some of these other ones. Some of these circles are not tangent to each other. It's like when there's overlap, like this circle and this circle here, they have overlap. But there is such a case where you could have internally tangent circles, where a circle's inside another one, perfect at the edge. It doesn't look like I have a great picture of that one there, but let me show you the second one that I had. This one just had the same thing. I showed you pictures of the spirograph yesterday, so it doesn't look like I have a really great of internal, an interior tangent circles. But here's a bike from the movie. The movie is called Premium Rush. That was the movie. It's basically just a road bike. Has multiple gears to it, and the idea is that the whole point of the movie was like delivering mail and stuff, and they were talking about how bicycling is kind of the way to go in New York. But the idea is that, you know, the gear in the front, if this is bigger than the back of the bike, you go faster, right? So the least amount of pedals. So that's why on some of these bikes have different gearing ratios, so it stretches out the cable, so it makes this back one a little bit wider, so it almost matches this. So the number of pedals is the same as the distance in the back. But the bigger this sprocket was, I was telling you, the faster the bike would go because the back one's really tiny. So it's called a fixed gear ratio bike. Well, this is the excessiveness of what they talked about in the movie. And I know it's comically big, and so this is one of his project bikes he was working on. Okay, they made the gear right where your foot is, the pedal, the number of teeth on the actual plate. There was like 104 teeth on that plate, which is like excessively big. It's like almost twice or 3 times as big as a normal bicycle pedal. And the idea is that if this is big enough that you could go insanely fast, because every time this spins around, it spins the back gear in the back of the bike the same distance. So, you know, this is maybe 2.5 feet around. Well, this one in the back is really tiny, but it also has to spin 2.5 feet around, so it has to do multiple spins to match it. And so the idea of this bike in particular is the one that I think they used in the movie itself, but it was a project bike. They talked about it online, and they had this big article about the actual movie and this bike itself, and that's the only reason why I remember it as well, is that this bike actually set a record. It could go over 100 miles an hour easily, like just by normal pedaling. Now it's difficult if you get to a hill because it's fixed ratio, you can't change down the gears, but it's insanely fast in flat level surfaces. And that was kind of the concept, and I thought it was kind of a cool picture of how you could see that. So, a little excessive, a little crazy, but I thought it was kind of cool. Okay. Now let's close those. Okay. Make sense? Alright, here's what I like to do. Okay, I'm going to hand you a note card. On your note card, I'd like you to put your name and your period and the date today. The date is the 2nd today. I want to see kind of where we're sitting. See if you feel comfortable with the homework before we get to it. I get it. Well, all right. 3 questions. This is not a pop quiz. This is just, I want to see where we're sitting. I want to see kind of where you're at right now. Can you do this? Do you feel comfortable with the homework? So here we go. First question. Like a little 5-minute check kind of thing. I want you to find X. I don't know why I said BC there. It's awkward. You see, it's V. I want you to try to find V. Give me a little bit of time here, see if you can find it. find VU, or X in that case. Okay, are we good so far? Okay, all right, next. Okay, let me zoom out here on this one. Okay, I would like you to try to sketch the following. So I want you to sketch two circles that are externally tangent to each other. So hopefully you know what that definition means. Externally tangent circles. Once you have that, I'd like you to draw a tangent line to both. Any type of tangent line. So once you have your tangent line to both, I want you to classify that tangent line. There's two types of tangent lines to circles like that. I want two circles that are externally tangent. So you have to draw a tangent line to both, and then describe that classification of that tangent line. There's two types of tangents. So again, you're drawing, you're sketching. Yeah, this is not a pop quiz, just kind of see where you're at. See if you can remember some of the stuff we talked about last couple days. So you have to describe that type of tangent. There's two types of tangents. Okay, are we good? Everyone had a chance to draw it? Label it. Okay, last picture of the day, last picture. I want to see kind of where you're at. Okay, on this one, I want you to find X on the picture, find X, and then also find the perimeter of the object. Now once you have this all and you have it completed, make sure name, date, period's on there. I have that on top of your card. I'm going to collect them. Let's see where we're sitting. you're done, name on it. I'm gonna walk around, I'm gonna collect. Alright, let's get rid of that. Let's see. Boom. Let's get rid of this. Drag this over. Alright, here's your homework today. Zoom in here. Okay, due Friday. Due Friday. Okay, just a reminder, because we have about 7 minutes left here. Next period, period 3, you guys are going to be voting for student council members. So whatever class you go to, kind of make sure you have your Chromebook out, all the good stuff. Just make sure, all the teachers should explain it, but when you vote, you got to make sure you're logged into your class only. So you're going to only vote for, like if you're a sophomore, you're only going to vote for sophomores, that type of thing. Don't be logged into the wrong test. But then also make sure that when you're voting, there's certain people that ran for a certain position. You can click their name. If you're not going to vote for the person that's running for that particular spot, there's an option for a write-in. But you have to click, there's a little button that says, the person's name, or below it says, I choose to do a write-in. That's the option you have to click, and then write the person that you would like to vote for. Okay. Some people in the last ballot that we did for the student body pres, they voted for the candidate, and then they did a write-in as well. That doesn't make any sense if you're choosing one or the other. Does that make sense to you guys? Some people were like choosing to do write-ins and they voted for the person. You don't need to do that. It's double up and we have to throw those ballots away. So, it's pretty easy. So, you either choose the person that's on the spot or you choose a write-in, you have to write that person in that you'd want.